Good day, everyone. Once again, this is Magnificent Educational International Consult, and we are going to be treating problem analysis on the previous topic we treated, which is ideal gas law. So, if you haven't watched that lecture, you can click on the link above to refer you to the lecture and kindly watch it before you are able to follow up with the juice. Okay, good. So we have a number of questions already written out, extracted from the recommended text, and some past question extract on JUPEB. So we have these questions there, 7 problems, and we're going to be analyzing them now. So let's go right there. So problem analysis on ideal gas. Let's look at the first problem. So problem analysis 1, problem analysis 1. So one thing is that before you start solving any question as a physics student, you should be able to tell and ask yourself what strategy will be suitable to be able to get the correct answer to a given question. So now let's look at what problem 1 says. And one of the things you should learn to do is to extract your parameters with their units. Okay, so problem 1 says here that a mass of oxygen occupies 0.020 meter cube. Occupies here tells you that it's actually something that has to do with quantity, and that tells you that we're talking about the volume parameter. So a mass of oxygen occupies 0.020 meter cube at ATP. So let's come here and put that down in our parameter. So we have volume was 0.0 what? We have 0.020 meter cube. Yes, so that's the volume, and they say that it was occupying this volume at an ATP of 110 kilopascal and 5 degrees Celsius. 110 kilopascal. So we are looking at pressure is 101. It's not 110 rather, 101 kilopascal is what was there, and they said the temperature was 5.0 degree Celsius. So they are trying to tell us that when the volume was 0.02 meter cube, that it was at a situation where the pressure was 101 kilopascal, which is actually the normal atmospheric pressure, and 5.0 degrees Celsius. Okay, let's see what happened. They now asked us to determine its volume if its pressure is increased to 108 kilopascal. So what will be the volume when? What will be the volume? That means we are looking for a volume. So this is situation 1. So we label them 1, V1, P1, T1. So this is situation 2. That is what will be the volume when the pressure P2 is what? So they said when the pressure is 108 kilopascal, pressure 108 kilopascal, and the temperature, as stated there, is 30 degrees Celsius. So I've just helped us extract the parameters in that question. So let's look at what we have here. We know that here we are given V1, P1, T1 and V2, P2, T2. Automatically, we know that this links us with the general gas equation, which is GGE, the general gas equation. So V1, P1 over T1 is equals to V2, P2 over T2. We know that this is our formula of relationship. But before I will solve, I need you guys to look at the parameters very well. Remember that we said never ever solve any gas law problem making use of temperature in degrees Celsius. Any unit of pressure works, but degrees Celsius does not work for temperature. So how do we convert this thing to Kelvin? Plus 273. Plus 273. So when we add 273 to this, it gives me 278 Kelvin. Why this one gives me 303 Kelvin. So what are we looking for? V2. So we should make the V2 the subject of formulae, and that gives us what? We are going to be having V2 is equals to V1 P1 T2 divided by T1 P2. So automatically there I have V2 is equals to what's our V1? I have 0.02 times what's our P1? 101, and what's our T2? 303. All divided by T1, which is 278 times what our P2 108. So automatically our V1 will now be our V2 rather, which we are looking for, will now be equal to let me quickly grab the calculator there. So what we are going to be having on our numerator side, we have 0.02 times 101. You can punch it in your calculator too. Multiply by 303. That gives us 612.06 as the numerator, and our denominator there is 278 multiplied by 108, and that gives us 30,024. So when we divide these two things together, we'll be having 612.8 divided by 30,024, and that gives us a new volume of 0.0204. Yeah, and what unit are we dealing with? Meter cube. So meter cube. So that's the case. As you can see, it's just a slight change in pressure that actually occurred. So I wasn't expecting a large change in the volume. So the initial volume was just 0.020, and here we're having just an increase to 0.204. So that is that for that. That's that for that. So you can as well also make sure you punch all these things in the calculator, you understand, in case of any technical errors. Okay, good. Problem analysis 2. Problem analysis 2. Yeah. So in problem analysis, question number 2, we said the density of nitrogen is 1.25 kilogram per meter cube. The density of nitrogen is 1.25 kilogram per meter cube. So this is one of the important parameters here, and its density. You can see the unit at STP, that's standard temperature and pressure. So what we are trying to say is that nitrogen had a density. So I'm saying the density of nitrogen. This is how we represent nitrogen density. We use this symbol, which is real. So it's equal to what? It's equal to what? What do we have there? 1.25 kilogram. So we're having 1.25 kilogram per meter cube. And they said it's at STP, right? So that means the temperature and the pressure are standard. And that means standard temperature is 273. Standard pressure is, it depends on what we have as our other unit. So I can use 760 millimeter mercury. I can use 101, depending on, okay, yes, so give it to us in millimeter mercury. So that means I'll be using 760 millimeter mercury as my pressure. So I have 760 millimeter mercury. That's our parameter 1. That's serves as our parameter 1. So parameter 2 now. So we know that density of nitrogen, I'll call it P1. The initial density of nitrogen at standard temperature and pressure was this. So the density, let's see what the question will now say. The now asks us determine the density. So we're looking for the new density. Let me highlight it with red. We are looking for the new density. So the density of nitrogen when the temperature is now 42 and this one is 730. So let's come here now. So we are looking for density now. That is density 2 of that nitrogen when the temperature, which I can call T2. Let's call it this one situation 1, T2 and P2. The temperature and pressure was 730 given to us in the question. And I think the temperature was 42 degrees Celsius. So we have temperature 42 degrees Celsius. So this is our problem there. Now, if you look at this there is no law amongst the law we treated that connects density, density, temperature, and pressure all at the same time. But we are working with physics and we have to learn to analyze. Let's ask ourselves a question. What is density? Density is mass over volume, right? And that means from this formula here, we can conclude that volume is equal to what? Mass M over density. So we know already that from our expression of density, we can actually bring out volume. And volume is one of the parameters we use in ideal gas flow. And that's what we are going to be doing. So it means that for this case scenario where I'm having density to be like this, it means that volume V1 should be equal to, remember that volume is mass over density, should be equal to M over this density, which is 1.25. Remember that we're working in kilogram per meter cube. So it means that the mass is in kilogram and the density here, which I wrote, is the one that is kilogram per meter cube, and my volume will be gotten in meter cube. You understand? Kilogram per meter cube. So my volume is in meter cube, my mass is in kilogram. So V1 is now, because we've deduced there that volume is mass over density, so it means that V1 should be mass over density 1, which is this value. Okay, let's do the same for this one now. V2 therefore should be equal to mass over density 2, which we have not gotten yet. So what we will now do now, we will recall ourselves that normally P1 V1 over T1 is equal to what? P2 V2 over T2. Anywhere we see V, let's put the parameters that we already extracted. But first of all, what are we looking at for? We are looking for what? We are looking for the second density, this one, which is under the V2. So let's quickly put all these parameters inside here. That's, I'm saying, substitute V1 as M over this. So we're going to carry it and put in this place for V1. And I'll carry this parameter also. This one I carried it there. And I'll carry this parameter also and substitute it as my V2. So that we can have a new expression. So the new expression that we'll be obtaining will look much like this. P1, instead of writing V1, I'm writing M over 1.25 divided by T1, which is equals to P2. Then instead of writing V2, I'm writing M over real 2, which is what we're looking for, divided by T2. That's what we're doing. So when we solve this stuff here mathematically to make them look more simplified, it means that what we're having here is P1M divided by 1.25 times T1, which is the same thing as P2M divided by real 2T2. It's just basic mathematics that we are solving. Basic mathematics. All these things are normal analysis. So M here is constant. That's the thing. The mass of the material is usually constant. That's why you also say when the fixed mass of gas, that if the volume of the fixed mass of gas is directly proportional, so the mass is constant, is fixed. So M can easily cancel M. So this formula remains P1 over 1.25 times T1 is equals to P2 divided by real 2 T2. What are we looking for? We are looking for real 2. Make real 2, that is the second density, the subject of formula. What do we have? This will now be equal to what? 1.25 times T1 times P2 divided by P1 times T2. It's basic, is your normal cross multiplication and then dividing both sides. So let's now substitute all the parameters that we have here inside this place. So density 2 now is equal to 1.25 times what's T1? 273 times what's P2? 730 divided by what's our P1? 760 times what's our T2? 42. So our real 2 now will give us, where's my calculator? Let me quickly use that. So we have 1.25 times 273 times 730. Our numerator value settles for 295. Settles for 295. I'm coming. You're having 249,112.5 divided by, so our denominator value here now gives us 760 times 42, and that gives me 31,920. So you have this now. So when we divide it, it will give us the density now. So we're having 249,112.5 divided by 31,920. And that gives us 7.8 84. That's 7.804 rather. And what is the unit of what we got? Like I said earlier, since they gave us this in this, so we got ours also in that same unit. Because I didn't do any conversion. So that's the density. And I think that's what they asked us for. We should look for the density of nitrogen. It simply means that the density of nitrogen at 42 degrees Celsius and 730 okay. Just like I used to say, remember that we were given our temperature in degree Celsius. So we're meant to convert this degree Celsius. So we're having plus 273. The common errors that people make in the exam hall, you can see it's very, very common and very easy to make. So good. So when we convert this back to what do you call it, Kelvin, what are we going to be having? We'll be having 300 and 15 rather. Yes, 273 plus 42. Plus 42, yeah. 315. So what we are meant to be having here is 315. 315. So that's a common error. You can see that now. So never work with your temperature in what do you call it, degree Celsius. You find out that the answer will be different from this. So we are having the denominator side here. This is still going to be the same because we didn't. We already worked with our standard temperature in Kelvin, 273. So this is where there will be issues. So we are having 760 multiplied by 315, and that gives us 239,400. Yes, this is an appreciable number for a density now. So I'm having 249,112.5 divided by 239,400. Yes, so that gives us a correct answer of 1.041 approximately, and that's the answer to this question. So that's it. So your density 2 is that value. It means that the density of nitrogen under these two conditions will be 1.041. So that's that for that. So let's look at problem analysis 3. Problem analysis 3. Problem analysis 3. So here now, they said a sample, these questions are not complex, a sample of oxygen has a volume of 225 mil. Mil is equivalent to centimeter cube actually. Mil when its pressure is 1.12 atm. Let's put down the parameters. A sample of oxygen gas has a volume. So volume V1 225 V1 225 mil, and they gave us the P1, that's the pressure one. They said that the pressure one is 1.12 atm. Yes. Then they also said that what will be the volume of the gas? What will be, that means V2. What will be the volume of the gas? Yes. And they said what will be the volume of the gas at a pressure of 0.98. So they reduced the pressure 0.98. What do you think we should be having? Before the pressure was 1.12, pressure has reduced. So we should be expecting a volume that is higher, right? So our answer has to be greater than 225 because we know that this is Boyle's law at work. So what does Boyle's law say? V1 P1 should be equal to what? V2 P2. What are we looking for? V2, right? So V2 is equal to V1 P1 over what? P2. And then we're having V2 is equal to what? What's my V1? 225 mil. So the answer I'm going to get must be in mil. And what's my P1? 1.12 divided by what's my P2? 0.98. So V2 now is equal to, using the calculator now, we're having 225 times 1.12. That gives me 252. So I have 252 divided by 0.98. And therefore V2 is equals to, divided by 0.98. I have 257. 257.1. Yes. So that was a mil because we were given the previous volume in mil. So you can see that it's actually greater than the former volume. So when pressure reduced, we actually should be expecting an increase in volume. It is consistent. So our answer is consistent. So let's go for problem analysis 4. Problem analysis 4. Yes, let's look at this. You know, the more problem you solve, the greater your ability to be able to be consistent when solving. That's why in Magnificent Educational Consult we have our drill session where we solve 200 questions, 150 questions, 300 questions on a particular concept. It's just aimed at gaining mastery in that concept. It builds you and makes you certified enough to be able to write the JUPEB exam as a scholar, somebody who is aiming to be able to to be able to get 3 A's. That's 16 points in total. It's very possible. It's all about practice. All right. So we have here now that a gas occupies a volume of 400 centimeter cube. A gas occupies a volume of what? 400 centimeter cube at 0 degrees Celsius and 780 millimeter mercury. So I have here now V1, P1, T1. They give us the 3 parameters. They said that the gas occupies a volume of 400 centimeter cube. So I'm working with centimeter cube here. 400, right? 400 centimeter cube. And then we have a temperature of 0 degrees Celsius. 0 degrees Celsius for the temperature. Let's quickly convert this thing into Kelvin. That's my advice. When you're in the exam hall, whenever you see that they give you temperature in degrees Celsius, convert it fast to Kelvin so you don't go and forget and start using the temperature in degrees Celsius. Like just what just happened to even me myself earlier. It's nobody can evade such an error. You understand? So make sure you avoid it by doing your conversion immediately while writing your parameters. So here now you know that this is 273 Kelvin. Yes. So they said the pressure is 780 millimeter mercury. 780 millimeter mercury as first scenario. So our second scenario here, we are going to be having a V2, P2, and T2. Let's see what they say. They said, what volume in liters? That is very important there. What volume in liters? So if you have not watched our measurement and unit lecture, try to do so. Try to do so. Because that's when you will learn how to convert from one unit to another unit. But I will help us now. One thing you must know is that 1000 centimeter cube is equal to 1 dm cube. And this 1 dm cube is the same thing as saying, let me say equivalent to 1 liters that they're asking for. So that's like saying 1000 centimeter cube is 1 liter. So you should know that now. So that's what we're going to be using for the conversion. So what volume will it occupy at 80 degrees Celsius? So my T2 is 80 degrees Celsius. Degrees Celsius, not a friend. Let's convert it. 273 to absolute, and then it should be giving me 353 Kelvin. All right, our P2 there is 780 millimeter mercury. Wow. So the P2 did not change. If you look at it, the P2 did not change. P1 was 780, P2 is 780. That means we are saying that P1 the pressure is constant. The pressure did not change. So it's actually advisable we can just use our Charles law. That's V and T, since pressure is the same. But even if you use your general gas law, you're going to get the same answer. You understand? But just to avoid stress, we'll be using Charles law since pressure did not change. All right. So we will solve normally using centimeter cube, and probably when we get our final answer, we can convert our final answer into liters, which is dm cube. Or you can decide you want to convert this 400 centimeter cube now into liters, and that gives you divided by 1000, because this is the conversion. Divided by 1000, that gives you 0.4 liters. So if I want to use the 0.4 liters like this, it simply means that I will just find the volume without conversion. So that's what we're going to do now. So automatically, we are looking for the volume. So V1 over T1 is equals to V2 over T2. And automatically, what do we have? V1, and what are we looking for? V2. So let me make V2 the subject formula. V2 is going to be equal to V1 T2 divided by T1. Normal basic mathematics. So V2 now gives me, what are V1? 0.4 liters is what I'm using now. So I'm getting my answer in liters directly, which is what was inquired of us. Multiplied by what now? By T2, which is this, 353 Kelvin, divided by T1, which is 278 Kelvin. All right, so punching that into our calculator now. Punching that into our calculator now, we have a 0.4 multiplied by 353, which gives me 141.2. Then I divide it by 278. Our final answer for volume is 0.508 liters. And if you agree with me, the answer is consistent. It's a consistent answer. What do I mean by consistent answer? Our temperature went from 273 to 353. That means it increased. I know that whenever you increase temperature, according to Boyle's law, your volume is meant to increase. So our volume increased from 0.4 to 0.508. So it's a consistent value. So that's how to solve analytical problems when in the hall. You have to be working with precision. You have to be working with accuracy. You have to be able to forecast your answers even while solving. You need to know that the answer I'm supposed to get should be greater than this because of this law that governs this principle. That is how this thing works. All right, let's go for the next problem now. I won't be needing this anymore. So problem 5. So let's see what problem 5 says here. The gauge pressure. Now, this is where you learn something new. You know, here at Magnificent Educational International Consult, we magnify the concept. We explain this concept so that you can become the concept yourself. It looks like you are a living concept. You understand? So that's basically our aim. The gauge pressure in a car tire is 305 kilopascal. 305 kilopascal, right? When its temperature is 15 degrees Celsius. After running at high speed, the tire has heated up and its gauge pressure is 360 kilopascal. What is the temperature of the gas in the tire? Assume ATP to be 101. Very, very direct, very important, but you need to pay rapt attention to this. Now, gauge pressure there. You said the gauge pressure in a car tire is 305. So pressure in the tire, let's just call that P1. It's 305 kilopascal, right? When its temperature is 15. So T1 is 15 degrees Celsius after running at high speed, and they said it gets heated up, right? So when it gets heated up, you know, whenever it gets heated up, that means temperature is rising. And when temperature rises, pressure has to go up. That's pressure law. So they said it gets heated up and its gauge pressure is now, so P2 now is now 360 kilopascal. Yes, that's what they said. So the question is what? The question is, what is then the temperature of the gas in the tire? So we are looking for the T2. You understand? Because they said at this temperature, this was the pressure, but now it got heated up and the pressure is now this. So what's that new temperature now? Good. Many students will now rush and say, wow, it's a very simple question. It's yes, very true. This is V1 over T. Sorry, what we're using here is our Gay-Lussac's law, which is P is directly proportional to T. And then you have P is equals to KT as usual. And then you now have what? K is equals to P over T. Remember those things. P1 over T1 is equals to P2 over T2, which is very true. This is what we're using. Now, they will now start substituting direct. And when you substitute this parameter direct, you are wrong. Because whenever you hear about gauge pressure is not the actual pressure. Gauge pressure is not the actual pressure. Gauge pressure is the difference between the actual pressure and the atmospheric pressure. So students, try to make sure you are careful whenever you are solving questions where they made mention of the word gauge pressure. You understand? I don't think we have come across such a question like that where they mentioned gauge pressure here. Is there any question like that? No. We've not come across a question where I think this is the first question we are solving where they are mentioning something like gauge pressure, and that's why I need you guys to really pay attention to it. So we have this now. So it means that we have to convert all our gauge pressures to actual pressure. And I told you now that the gauge pressure is equal to actual pressure minus atmospheric pressure. So that is the formula for gauge pressure. So how do we get our actual pressure now? The actual pressure now is actually supposed to be gauge pressure plus the atmospheric pressure. Are we getting it now? So what is going to be the pressure we are using here? This is a gauge pressure, right? So our P1, this is a gauge pressure. This is not actually the real P1. This is a gauge pressure. So the P1 should be, that's the actual pressure, that's the actual P1 should be this gauge pressure plus atmospheric pressure, which is what? 101 kilopascal. It's constant. Do you see that now? And the same thing applies to this because they also told you that this is gauge pressure, so actual pressure 101 kilopascal. Convert this temperature to Kelvin, 273, and that gives me 288, if I'm not mistaken. Yes, 288 Kelvin. While this one here gives us how many? This gives us 406 up here, kilopascal, and this one here gives us what? 461 kilopascal. Yes. So good. We've applied this concept. Try to make sure you always remember this concept. Gauge pressure is equals to what? Actual pressure. It's the difference between the actual pressure and the atmospheric pressure within a confined gaseous system. So now we can now solve. What are we looking for? T2. So from here we know that T2 should be equal to T1 P2 divided by P1. So let's quickly substitute those values inside that what do you call it, into this formula. So T2 now gives us T1 is 288 multiplied by P2, which is 461, divided by P1, which is 406. Yeah. So let's divide that and see what we have. So we know that our answer is going to be in Kelvin. I look for temperature. So 288 times 461 is 132,768, and then we divide it by 406. So what we have is 327 Kelvin. 327 Kelvin. So our T2 is 327 Kelvin approximately. So is it a consistent answer? Let's check. Pressure will increased from 406 to 461, and we know that when pressure increases, temperature should increase. So automatically, if you check it, our temperature was 288 and it increased to 327. So it's consistent. It is consistent. It's a consistent answer. So let's go for problem analysis 6. Problem analysis 6. Problem analysis for number 6. So when we look at number 6 here, they said gas at room temperature and pressure is confined to a cylinder by a piston. Now the piston is now pushed in. You know, when you push a piston in, you are trying to increase the pressure so as to reduce the volume. You see, it's consistent. When I say so as to increase the pressure, now when you increase the pressure, you are reducing the volume. That's that demonstration we talked about in the first video. That's the theoretical part of this topic. So as to increase the pressure, which is reducing the volume to 1/8 of its original value. So what we are trying to say here is this. They said gas at room temperature, automatically they just told you now that P1 and T1 are 760. Are we working with millimeter mercury? Let's work with millimeter mercury. 760 millimeter mercury, that's standard pressure. Because they told us it's at room temperature and pressure. It's confined to a blah 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 and those kind of stuff. Okay, so we have 760 millimeter mercury, and I have my this one to be 25 degrees Celsius. You know, room temperature is 25 degrees Celsius. So add 273. I have what now? I have 298 Kelvin. So that's it. So gas at room temperature and pressure is confined to a cylinder by a piston. The piston is now pushed in so as to reduce the volume to 1/8. So you know, at this point here, it will have a particular volume that we call initial volume, right? Which we call V1. Yes, at this situation here, it has an initial volume we call V1 normally. So they're trying to tell us that now that when they change that pressure, the volume reduced to 1/8 of its original. That means we're saying that V2, the new volume, was 1/8 the former volume. It's reduced to, I mean, they said it reduced by 1/8. Please take note. I mean, they said it's reduced by 1/8. That means your V2 would have been equal to V1 minus 1/8 V1. That's what it would have been equal to. Assuming they said by. Assuming they said by. You get, but now they said it reduced to. So the new volume was actually 1/8 of the initial volume. Good. So after the gas temperature has returned to its room temperature, what is the gauge pressure of the gas in kilopascal? So we're not even actually solving any serious thing here. So we're looking for the gauge pressure. Gauge pressure is what we're looking for. Gauge pressure of the gas in kPa. So since they want us to get it in kPa, then we should know that the normal atmospheric pressure in kPa is 101 kPa. We've been using that to solve already earlier on. You understand that now? We've been using that to solve in earlier lecture. So we know that this is the atmospheric pressure. And they're asking us to find the gauge pressure. What that tells you is the gauge pressure. Your gauge pressure is supposed to be equal to the what? I said it earlier. Gauge pressure should be equal to actual pressure minus what? Atmospheric pressure. Yes. So that's exactly what the question revolves around. So whenever you are given such a question, try to read the concept. The concept will speak to you, everything like that. Try to extract all the important parameters, and then you'll be able to get your answer. Everything was consistent. Pressure, the piston is now pushed in so as to reduce the volume. So you know that already pressure was going to do what? Increase. And then they said it reduced by 1/8 of its original value after the gas temperature has returned to room temperature. What is the gauge pressure of the gas in kilopascal? They say we should take the local ATM. Sorry, they say we take the local ATP, which is your atmospheric pressure, to be 760 millimeter mercury. So what do we do now? How do we go about solving this kind of a question? All you just need to do here is to just calculate your, what do you call it, your gauge pressure, which is obvious already. So the gauge pressure here now that we're going to be dealing with here is going to be our gauge pressure is going to be the actual pressure minus, we have the ATP that we're going to be using. It now depends on what value you want to use. If you want to work in millimeter mercury or want to work in what do you call it, in kilopascal. You understand? And they said we should work in kilopascal. So there's no point. I already know that the conversion of 760 millimeter mercury to what they call it, kilopascal will give you 101. It's standard. It's a standard. 760 is the standard pressure, which is equivalent to 101 kilopascal, which is equivalent to 1 ATM. You understand? So if you see this kind of stuff, they are interrelated. So I'm just doing minus what do you call it, 101 kilopascal. Yes. So if you now check something now, we know that normally P1, let me come here. P1, when P1 is 760 or 101 kilopascal, we know that our T1 is supposed to be its normal 273. That's standard temperature and pressure, right? But now they are not checking room temperature. So room temperature now is 25, which is the 298, Abi? 298 Kelvin. So what's going to be pressure at that point? That's what we need to first of all think of. So let's get this pressure in this place, and then we'll find out what we are doing. Here now, they said that the volume, let's call V1 V1 and call V2 1 all over what? 8 V1, right? All right, so that's what we're going to be working with. So I will use this space here to do this. So then now, based on what we have there now, we should know that we are going to be having a P1 V1 over T1 equal to P2 V2 over T2 using those parameters there. So our P1 there is 760, right? That's 101. So I'm having 101 times our V1 is V1 divided by T1 is 273 equals to P2 is what there now? P2 is what we are looking for, multiplied by V2, which is 1 over 8 V1, divided by T2, which is 298. V1 can cancel V1 from this side. So it means that P2 should be equal to 101 multiplied by 298, right? Divided by what? 273 times 1 over 8. That is how we will get the P2. But remember that we're getting this P2 now. That's the actual pressure. That's what we're looking for, like that. The actual pressure. So we're having 101 times 298, and that gives me 30,000. Let me just say multiply by 8 also. I'm solving everything together, then I'm dividing by 273. That gives me 881. That's 882. It gives me 882. 882, and we are working in kilopascal. 882 kilopascal. So automatically the actual pressure is 882 kilopascal. So what they ask us for is not the actual pressure, right? They ask us for the what? Gauge pressure. So what will be the gauge pressure now? Our gauge pressure is now this actual pressure 882 minus 101 kilopascal, right? And that gives us what? That gives us 781 kilopascal. So that is it. So the concepts are not complex. It's just a matter of you being able to extract your parameters correctly from this region. All right, let's go. Let's go. What can I use? Okay, let's solve here. Let's solve here. So this is the last question. Problem 7. So there now we have, they said a 3-liter tank, that is the volume, contains oxygen gas at 20 degrees Celsius and a gauge pressure of, you see they are now working with this gauge pressure thing so much, so you need to be used to it. So volume is 3 liters, let's call it V1, and they said contains oxygen gas at 20 degrees Celsius. T1 is 20 degrees Celsius. What did I tell you about anything degrees Celsius? We need to convert it immediately so that we don't forget. So that's 293 Kelvin. Yes. And a gauge pressure of what? Of this, right? Are we using this? We are not going to use this because this is a gauge pressure. This is not actual pressure. In our Boyle's formula, it is actually the actual pressure we work with. This one, they ask us to get gauge pressure. That's why I've had to get the actual pressure first, then convert to gauge pressure by subtracting atmospheric pressure. But here now we have gauge pressure, we have to convert it to actual pressure. How do you get actual pressure? Actual pressure is equal to gauge pressure plus atmospheric pressure. Yes. So I'm going to come here and write our P1 should now be equal to this gauge pressure here. Will you agree with that? This gauge pressure here is the same thing as, if you convert this to 25 times 10 to the power of 6, it's the same thing as saying 2.5 times 10 raised to the power of 6, Abi? Pascal. And we know that therefore that this 2.5 times 10 to the power of 6 is equivalent to 2.5 times 10 raised to the power of 3 kilopascal, because kilo is times 10 raised to the power of 3. So I remove times 10 raised to the power of 3 from here. Are we getting the concept here now? Which is the same thing as saying 250 kilopascal. Do you see how very easy science can become? So here we are saying that we are working with 250 kilopascal plus what? Plus what? 250 kilopascal plus the atmospheric pressure, right? Because that's what we are trying to do. We are trying to get our actual pressure. So plus atmospheric pressure 101 kilopascal. And that gives us how many? 351 kilopascal. All right. So let's check what mass of oxygen. Wow. What mass of oxygen? We are looking for mass here. But whenever you see things like this, don't be scared, because we know that volume can bring out mass. Many things can bring out the mass of a substance eventually. You understand? So we will still see what we're going to do. So what mass? Mass is question mark. What mass of oxygen is in the tank? What mass of oxygen is in the tank? The molecular mass of oxygen is 32. That's what they just told us now. So that's capital letter N is 32. Molecular mass of oxygen is 32. Assume ATP, atmospheric pressure, to be this. We've worked with that already when we're getting our gauge pressure. Okay, what do we do here? This is not even dealing with V1, P1 and all those things. What we want us to do is PV equals to nRT. Yeah. PV equals to nRT is what it wants us to work with. Yes. So what is our P? We have it here. What is our V? We don't. Do we have our V? Yes, 3 liters. Then what's our N? Our N, we don't have it, but we know that N means moles. N is moles, and moles is mass over what? Molar mass, right? So that was why they told us to find the mass. So instead of writing mole, anywhere we see mole, we write M over capital letter M. So it means that this ideal gas equation can be rewritten as PV equals to what? M all over M RC. Can you see how simple things can become? Very, very direct, non-complex, very simple, very easy. So we are looking for the mass. We know our T is already given to us as 293 Abi. Our R is here now. So one of the things that I will literally advise at this point in time is that your R, remember we said R can be 0.0821 when you are working with ATM and liters, right? But here now we are not working with ATM, true or false? So I will literally advise that we convert these parameters here to ATM, although it might not even affect the what they call the expression. But so you get to a good you get used to good habits in solving physics. Try to make sure you do your conversions. So what am I trying to say now? This what is it? This 2.6, this 250 kilopascal, we know it is equivalent to how many ATM? 1 ATM, Abi. Good, 1 ATM. Because sorry, I said we know that 101 kilopascal is equivalent to what? 1 ATM. So therefore 250 kilopascal, which is this we got, this one that they gave us in the question, Abi. 250 kilopascal should be equivalent to X. So how do you get that now? It means that our X is what? 250 divided by 101. And that gives you how many? 2.48. So we're having X equals 2.48 ATM. So let's use that now. So this 250 here, I want to replace it with 2.48. So I'm saying that my pressure is equals to 2.48 plus this 101 is 1, Abi, which is how many? 3.48 ATM. So 3.48 ATM. Yes. Why am I doing that? Because for me to use these units, I need to be working with my pressure in ATM, my volume in liters, which has been given to us already. I get me now, then the remaining in mole and all those things. So let's quickly do that now. So our P is 3.48 multiplied by a volume of 3 is equals to M that we are looking for over 32 that we are giving molar mass multiplied by 0.0821 times temperature, which is what? 351. And therefore we can solve with this. 3.48 times 3 gives us how many? 3.48 times 3 gives us how many? 10.44. We have 10.44 here. 10.44 equal to, what do we have? 0.0821 times 351. 0.0821 times 351. 28 point what? Divided by 32. Divided by 32 gives us, we have 0.9. So in this place here, I'm having 0.9 M. Are you getting me now? By the time you solve all this one divided by this, it gives you 0.9 M. By looking for M, divide both sides by 0.9. By 0.9. So our M is equals to what now? 11.6. Now, this 11.6, is it kilogram, is it gram, or what? What do you think we are working with? Is it kilogram or gram that we're working with? Yes? Kilogram or gram? If you look at our, what they call it here, the 32 we used, you can see that they wrote 32 kilogram per kilomole. But don't be confused. This kilo can cancel this kilo. So what this thing here means is 32 gram per mole. So we just got our answer in gram. So that is the answer to that question. So this is Magnificent Educational International Consult. We've just finished analyzing 7 questions and problems from the recommended text for the A-level exam. And I believe it's clear. For regions where you still have confusions or questions, you can actually ask your question by commenting down in the comment section, and then we will respond to you duly. So take care and do have a good day.